Okay, so rates of change and limits. So the very first thing we're going to talk about is rate of change. So let's say I drop a penny from the rooftop of the high school. We want to figure out the average speed during the first 2 seconds of free fall. So generally speaking, how do you figure out average speed?
Distance over time.
Yeah, it's the total distance divided by total time. Total time is going to be
Drop.
2. Total time is 2 seconds. Because the question is saying during the first 2 seconds of free fall. The total time is 2 seconds. With these word prompts, you don't need to copy down word for word. You can just summarize it. Just make sure you know what the key things are. Okay, so it's total distance divided by total time. Now distance, whenever you drop anything, assuming like there's no wind and stuff like that, it's going to drop at that kind of rate. So in 1 second, it's going to travel 16 feet or 16 inches or whatever you're talking about. So 16 is actually the force of gravity on Earth.
The amount of mass doesn't affect this, right?
We're going to assume like there's no air. So like if we're in a vacuum.
Oh.
Yeah. Okay, so that's given. So y is your distance. Okay, y is your distance. And then t is time. So the distance traveled in 2 seconds is, you plug 2 into t. Squared is 4 times 16 minus the original placement. The original, place of the rock. When the rock is in its original place, what's the time? 0. That's why I plugged 0 in there. Divided by total time, 2 seconds minus 0. And then we get 32 feet per second. All right, any questions there? Okay, that's pretty simple. It's pretty standard. You should have been able to do this without me helping you at all. Anyone wants to comment down? Okay, now we're going to talk about instantaneous speed. This one we were talking about average speed. Okay, average speed is the speed over a certain amount of time. Instantaneous speed is kind of the speed of anything at that instant, at that moment. So, speed of an object at any given instant of time. Now, instantaneous speed, the speed at any given time, is not the same thing as average speed. It's not the same thing as average speed. Because we know that it starts at 0, then it goes to 1, then it goes to 2, then it goes to 3, and so on. So average speed is constantly changing. We're looking for speed at a particular moment. Is it red? Alright, questions so far? Any questions as to what instantaneous speed is? Alright. Okay, so we're going to find the speed of the penny when time is 2 seconds. So your answer should be different here, right? Because we're not looking for average speed, we're looking for instantaneous speed. So speed right at 2 seconds, what's the speed of the penny? Now to find it, so here's 2 seconds. Right? There's kind of no way of figuring it out at 2 seconds exactly without having something to compare it to. So we're going to compare it to a speed a little bit more than 2 seconds. So a little bit more than 2 seconds, we're going to add h. H is slightly more than 2. So the shortest amount of time you can think of, we're going to add that to 2. And then we're actually going to take the average of those two speeds that are so close together. We can just say that that was the speed of this.
Can we explain?
Yeah. So, okay, so let's say I drop the penny. At 2 seconds, we know that it's a certain speed. But without something to compare it to, without something to average it out with, there's no way of us finding it. So we're going to average it with kind of the next instant. Right after 2 seconds, we're going to measure. So not 3 seconds because that's too far apart, not 2.5, but right after 2 seconds. Like instantly after 2. Does that make sense, kind of? Alright, it's a little confusing at first, but after you see the entire problem go through, it'll make sense. So we're still going to find the average. So this is time 1, and this is time 2. We're going to take the second time, so we're plugging it into the same thing. The second time is 2 plus h, or 2 seconds plus h. We're going to square like we did, times 16, minus the original time. The original in this case is 2 seconds, right? It's not at the origin. We're looking at 2 seconds. And then total time is, this time minus this time, which is why we just have h. The 2 plus h minus 2 will give us just h. And then all we're going to do is simplify this. So we're going to FOIL 2 plus h, square 2, and then go ahead and simplify this as best as you can. Any questions up to this point here? We can cancel out some of the h's. So we get 64 plus 16h. Any questions as to how I got to this part? Okay, so this is the speed. But we don't really know what that means yet, because we don't know what h is. What does h stand for? Exactly, it's that little extra time that we added on after 2. This is what we're going to plug in for h, and this is kind of conceptually strange. Let's say, Superman was like right here, and he runs at lightning speed. And in an instant, he ends up over there. And I asked you, how much time did it take him to get from here to there? What would you say? Not the answer I'm looking for. How much time? Give me a number. What? Less than that.
0.1 second.
Smaller.
0.0000.
Smaller. No. Would you say that from here to here it's almost instant? So, what did you say?
0.
0. It took him 0 seconds to get from here to here. Does that make sense? So it's so fast, it's an instant, that from here to there takes in 0 seconds. That's actually what we're going to plug in for h. Because the time that we're measuring after 2 seconds is so fast, it's really 0.
But it can't really be just 0. It
Right.
has to be like
Really
Right, it's not
tiny.
actually 0, but it's so small
that you don't even count it.
that we can just say it's 0.
Okay.
Right, because it's so small. Because as h gets smaller, like if you said h was 0.1, you multiplied it, it's a pretty small number already, but if you said h was 0.00000, let's say 10 zeros and then 1, this 16 is almost not even there anymore. And so it's so fast that we just say that that's 0.
And that's the answer?
Yeah, this is the answer. So at 2 seconds, it's going at 64 feet per second, which makes sense, right? Because the average speed from 0 to 2 was 32. We know it started at 0, so it has to end at 64 for the average to be 32. Any questions there? It's kind of cool though, huh? No? Okay, maybe not.
No.
Okay, any questions? Anyone wants to comment down?
So,
Yeah.
So basically, whichever one has an H, you just multiply it by 0?
You plug in 0.
Yeah.
Yeah.
So you leave whatever's left.
Basically, yeah. But you do need to simplify it first, right? Because you can't plug in 0 up here or here or here, right? Because you can't have 0 in the denominator. Yeah, I can.
Where's the 16 from?
This one?
Yeah.
It's from the previous page. Right there. This is given.
Oh, is that the formula?
Yeah, this is kind of like when you drop something, it's always going to be this formula.
So it's never going to change? Like 16 will never change?
Nope. It depends if you change the metric system. So this is feet per second. If you're talking about meters per second or something like that, then it's 32.
I don't understand how it works.
What works?
The two different formulas and how they relate to each other. Like I see it. I see like one is double the other, but I don't know how.
Like this formula?
No, like the ends like the 32 feet per second and then the 64 feet per second.
You don't understand why
Yeah.
64 and 32? Alright, so here's your rock, right?
Yeah.
You drop it, it ends up here.
Uh-huh.
What's the speed here at 0?
0.
0. We just found the speed of 64 here at 2 seconds, right? So the average speed, which is what we were looking for in example 1, has to be the average of these two,
Oh, okay.
right? And that's 32.
You can't see it you can't see
That's
that. Okay.
Alright, yeah.
So, is 16 always going to be the given for these problems?
Yeah. If it's talking about feet per second. Alright. Okay, so now let's talk about limits. So this is what limits tell us. This is what limit does for us. This is why we want to know it. Limits tells us how the output of a function behaves as the input approaches a particular value. So output is which variable, x or y? Okay, x is input, so output is y. So this tells us how y looks like as x comes closer to a number. It's telling us what the output looks like as the input is getting closer and closer and closer to a number. Okay, so let's look at sine x over x as an example. We're going to look at what's sine x over x as it gets closer and closer and closer to 0, what that looks like. Okay, so we're going to look at this function. We're going to see what happens as x gets closer and closer and closer to 0. Because obviously it can't be 0, right? But we're going to get so close to it, we're actually going to figure out what it is. So on your graphing calculator, you're going to go to graph. Alright, y equals. You're going to plug in sine of x divided by x. So you can plug that into y equals. If you don't have one with you, share with the person next to you, just so that you can see it. And then you hit graph.
What do we put in there?
Sine of x over x.
What should the mode be? Degree, right?
What should the what be?
Mine doesn't do anything.
Your fingers like small.
So if you want to zoom in, go to zoom, and then in, so it's 2. And then you just hit enter, and let's see what happens there. Alright, so it's 2 zoomed in, so let's zoom out a little bit. Let's go to window. For x min, let's go to -4. Let's go to -3.5. For x maximum, let's go to 3.5.
Yeah.
For y minimum, let's go to -1.5. So I'm just zooming out a little bit so I can get a picture of the graph. And y maximum, let's say 1.5. Okay, there's your graph now. Okay, that's a better looking graph. So when x approaches 0, what does it look like the graph is going to equal to?
1.
Yeah, when x approaches 0, here's 0. It looks like the graph is at 1. Or it looks like it's at 1. So because it's so close, and if you continue to zoom in at that point there, eventually there's going to be a hole. Eventually there's not going to be anything there. But because it's so close, we just say, as x approaches 0 of sine x over x, we're just going to say that that's 1. Okay, here's another proof of it. If you go to second table, and then if you scroll up a little bit just so you see some negatives and some positives, when x is 0, it says error, right? As it should, because you have 0 in the denominator. But if you look at the y values, it's getting closer and closer to 1. Getting closer and closer to 1. So we just say it's 1. Second table. Second graph. Hit the second button and then graph. Scroll up a little bit.
It's red batteries. Now.
Is it on red?
Yeah,
Or is it
no.
dead?
Huh? No, it's not dead yet. But
Okay, that's fine. We'll just go as long as we can.
okay.
Alright, any questions so far? So we say that the sine of x, and this is how it's going to be written, the limit as x approaches 0. So basically, if you're looking along the x-axis, as it goes closer and closer to 0 from both sides, or from the positive side and from the negative side, what number does it get closer and closer and closer to? Well, it gets closer and closer and closer to 1. Alright, any questions there? That's this one. Yeah, so the limit as x approaches 0 of sine x over x is equal to 1. So as we go towards 0 along the x-axis, your output, your function, is equal to 1.
So it never actually touches the 1?
Can't.
So it just stops right before 0.
It stops so close.
Starts right after 0.
After
Keep going.
Yeah,
So close.
but it's so close that we just
can't.
say it's 1. Alright, but yeah, no, that is actually what's going on.
But how would you
And-
find it without graphing?
How do you find it without graphing? That's why I graphed it for you guys. Because this is going to be one of those things you will eventually memorize. Some things in calculus you won't be able to do without graphing. Or it's just so much easier by looking at the graph. Alright, any questions with this? Okay, let's look at some properties of limits. So basically, if you have two things inside of a limit, you take the limit of both things. It's going to look a lot more complicated than it actually is. So if we have the limit of x squared plus x cubed, you just take the limit of x squared plus the limit of x cubed. Same thing with subtraction. So if you want to save some space, you can just put plus or minus here, plus or minus there, because it's the same rule. Same thing with multiplying. If you have x times y, right, the limit of x times y, you take the limit of x times the limit of y. Same thing with dividing, but with this one, I'll wait for you guys to copy it. For this fourth one, k, and that's this plus right there. K is the constant. Okay, so let's say you're taking the limit of 2x. You're really taking the limit of x and then multiplying it by 2. And then, of course, we'll look at some examples. Same thing with dividing. If you're dividing, I don't know, x divided by y, you do the limit of x, divide by the limit of y. And then finally, if you have an exponent, you can take the limit of the thing first, and then square it after that. Or do whatever exponent after that. Looks pretty complicated, but once you actually use it with numbers, it's almost the same thing as plugging in.
Are the third and fourth lines together?
No,
No, they're different, right?
yes, they're all different. So these are all different rules, all different properties.
What does the exponent say?
Just RS, R over S. It's just some variables. Yeah. Where? Under it, it says x equals c. So c is just some number that, depending on the problem, that's just going to be what you plug in. Alright, any questions so far?
I have a question about the fourth one.
This one?
Yeah.
Yeah.
Is there something about the constant?
Yeah, k is a constant,
Which
So-
is the, what?
which is just a number. So limit of, let's say, 2x is just the limit of x times 2.
Oh, okay.
And I'll show you this with numbers right after this slide. Anyone wants to comment down?
C is a constant.
C is also a constant. Alright, use the properties to find limits. Here's example 3a. Notice that we're going to leave it as a constant for now because I really do want you guys to understand how you plug it in. And that it's not really just substitution, even though it almost is. Okay, so if you add and subtract, if you're adding and subtracting inside the parentheses, what could you do with all of them? It's that first and second property.
Split it.
What's that first and second property say? Yeah, you just take the limit of all of them. So this is really the limit of x cubed plus the limit of 4x squared minus the limit of 3. No, it's not like log. It's a little different. Okay, and then all we do is take c, or whatever number this is for the problem, and you plug it into x. And then if you just have a constant, there is no x to plug it into, so it's just the number. And then that's it. And then, you know, if these were numbers, you just calculate that. All right, any questions there?
So why did limit change to C?
Because as x approaches c, so we take c and you actually plug it into the x. So as x approaches some number, we take that number and plug it in. Alright. With this one, if you don't want to, you don't need to write down the second step, because what I basically did was just I put limits in front of all of them. So it's the limit of x to the fourth plus the limit of x squared minus the limit of 1 divided by limit of x squared plus limit of 5. Alright, so it is a lot to write down. I think you guys are smart enough to understand that. Okay, any questions so far? When you show your work tonight, you don't need to do it this way. I'm only breaking it, down as much as I can, just so that it's very clear what's actually going on. From here, what would you do? Exactly, you just plug c into what? X. So you get c to the fourth plus c squared minus 1 over c squared plus, and what goes here in the last space? 5. Good, plus 5. Okay, any questions there? What's the copies now?
Just to make sure, the little x arrow C just means just plug in C into x, right?
Basically, but this is actually what's being said. So it's saying the limits as x approaches c. Yeah, so as x approaches some number. So in the sine example, it was as x approaches 0. Okay, Okay, go ahead and try this one yourself.
This is the same.
Is it the same thing?
Yeah.
Yeah.
Oh. Okay. Okay, anyone really need to do an example? Anyone want to do an example? I think this stuff is simple enough that you guys understand. You just plug it in. Okay. So let's actually try with numbers. So we got the limit as x approaches 3, and that's how you're going to say it. Okay, so the limit as x approaches 3 of x squared times 2 minus x. All you do is plug the 3 into the x. And then you calculate it. 3 squared is 9, 2 minus 3 is negative 1, you get negative 9. Let me show you what's actually going on, because I think you guys are just calculating without knowing what's up. So let's say, pretend this is the graph. Okay, I don't know what the graph actually looks like, but let's just say it looks something like, let's say it looks something like this. Let's say this right here is 3. As x approaches 3, your graph right here, that's negative 9. So this is saying as x approaches 3, so along the x-axis, as it's getting closer and closer to 3, your graph is negative 9. And then if you actually graph that on your graphing calculator, I don't know if this is what your graph's going to look like, but this part right here will be right. Okay, question?